Hey, hi, good morning, everyone. Good morning, friends. Right, so yesterday we have started a new module on machine learning, and welcome back to this particular session where we are going to learn the classification problems, the classification algorithms. So, in the previous session, we understood what exactly is, you know, classification, from where we have derived this word classification. And just give me a minute. Yes, right. So we has understood the concepts of machine learning. I mean, if you exactly understand, under machine learning we'll have types. Okay, we understood supervised, unsupervised, and reinforcement learning, the differences between the types, followed by, once after understanding the types of machine learning, we understood the types under supervised learning. Under supervised, there are two types. One is classification and the other one is regression. So, friends, what is the difference between classification algorithms and regression algorithms? When do we use classification and when do we use regression algorithms? Yes, I want everyone to interact here, okay, because let us understand how much did we grab as part of yesterday's session, and moreover, we'll make the session interactive. So when do we generally use classification and regression algorithms? What makes the difference between classification algorithm and a regression algorithm? Classification algorithms are generally used if you have discrete fixed values in y column. Good. Regression, it's opposite. If it is discrete here, under regression it will be continuous. That's it. Now tell me, naive Bayes is a classification algorithm or a regression algorithm? Does it fall under classification or regression? Okay, my friend says classification. In real time, generally naive is generally used for classification task. In order to classify the classes, we generally use naive Bayes algorithm as a classification algorithm, but that doesn't mean naive Bayes can be used only for classification. This can also be used for regression. I have discussed this point. Naive Bayes, KNN, decision tree. These three comes under classification algorithm. But these three algorithms are called as shallow techniques. Shallow techniques, which means these three algorithms can also be used for regression task. Even if the values under the y column are continuous, still we can use any one of these three algorithms for the specific problem. Okay, so that means we can also use naive Bayes for continuous data, not only for the classification, not only for the fixed values, we can also use it for continuous data. Good. Then what else did we discuss with respect to naive Bayes? Understood what exactly is naive Bayes? Yes. Naive Bayes works on a mathematical concept. It is probability. Okay, when you say probability, what is the formula for probability, friends? How do you define probability? Tell me the formula. Define probability. Simple. Interested events by total number of outcomes. Total number of outcomes. This represents probability. When you toss a coin, you'll get either head or tail. When you take a fair coin, I'm talking about fair coins. Okay, so when you toss a fair coin, either you'll get head or tail. So total outcomes. What are the total possible outcomes? It will be two, but you can get either head or tail. You cannot get both, right? So impossible. So probability of getting head will be 1 by 2. Probability of getting tail is also 1 by 2. We understood this example. Moreover, this is not a new topic that we are learning now. Okay, probably from 9th, 10th, even if you have opted for MPC, mathematics as a subject in your 11th, 12th standard, you'll have this probability as one of the topic in your mathematics subject. So probability is very important, especially if you want to learn machine learning, deep learning algorithms. This is very important. The main reason is majority of the algorithms use probability concepts, and one of the algorithm that uses probability concepts is Bayes. Okay, so we discussed probability. What are the properties of probability? I want everyone to keep your answers in the chat. Don't sit idle. What are the properties that we have understood? The range for probability, is 0 to 1. This is a property. Probability cannot be greater than 1 and less than 0. Okay. What is the second property? When you sum up all the probabilities for an event, you'll get the answer as 1. Summation of all the probabilities will be 1. Right? So these are the two important properties of probability, and everyone have to remember these two. Why? Because in the coming 10-15 minutes we are going to understand a use case with respect to neighbors. Okay, a small use case. So there, not only there, you can also understand how neighbors is actually using the concept of probability. So the properties are very important. Then we also understood the concept of conditional probability. Right? So what is conditional probability? This is probability we have understood. Conditional probability. Come on, guys. Okay. So conditional probability talks about at least two or more than two events. It's not like you go and work on a single event. Conditional probability, at least it is calculated for two or more than two events. We have understood. And if someone asks you what exactly is conditional probability, you can say it as probability of event B occurring given that knowledge, given the knowledge that event A has already happened. So that means out of the two events, one event has to be completed. Okay, then what is the probability of event B happening is nothing but conditional probability. And this is the formula for conditional probability. I hope you remember the example. We have understood the example with respect to playing cards. Right? So playing cards. There are 52 cards. We understood what are the different shapes we have in the playing cards. Heart, then club, spade, diamond. Okay. We have understood all these as part of conditional probability, and the formula says probability of B given A. That means you're going to calculate the probability of B that event A has already happened. Okay, so is given as probability of A and B This is nothing but P of A and B by P of A. What is the example that we have understood yesterday? We are going to calculate the probability of drawing a queen. So in 52 cards, you will have 4 queen cards with 4 shapes. Okay, given that already drawn card is diamond, so it should be a queen and it should be a diamond card. In 52 cards, how many diamond cards you'll have? 13. And how many queen diamond cards you'll have? Only one, given by 13. So this is the answer. We have understood, right? Yes. So today uh, we'll make our discussion a bit further. We'll go a bit further and we'll understand what is Bayes' theorem. What is Bayes' theorem? Bayes' theorem was calculated, the formula was derived from, conditional probability. Isn't it? Yes. So that is the reason we understood the concept of probability, then conditional probability. Using conditional probability, we are going to achieve this formula. Okay, so this represents Bayes' theorem, friends. Okay, so it is generally used to calculate the probability of a class, whether an instance belongs to a particular class or not. That's it. Okay, so how we are going to achieve this formula, we'll understand. Right? So, what is the formula for conditional probability? What is the formula for conditional probability? Conditional probability says if I have two events A and B, okay, and if I want to calculate probability of B, given A has already occurred, the formula says P of A and B divided by P of A. Okay, so this is the formula for conditional probability. I'll change my statement. In the previous case, we are trying to calculate probability of B given A. That means event A has already occurred in case 1. But this time, I want to calculate probability of A given B. Okay, that means event B has already occurred. Okay, now I'm trying to do, I'm trying to calculate probability of A. Then what will be my formula? My formula will be P of A and B divided by P of B. Am I right or wrong? So using these two formulas, can I derive it? Yes, obviously. How? So why don't you equate these two? How? Again, the question comes. So what is common here? Probability of A and B, probability of A and B. Both are same? Yes, in both the cases, in both the formulas, the numerator is same. So if I take probability of A and B is equals to probability of A and B, as they both are same, then what will be the formula? I'll cross multiply. Okay, so since I don't have anything, it will be 1. So I can write it as P of A multiplied by, okay, P of B given A. Then in the second formula, I'll do the same. What I'll get? P of B multiplied by P of A given B. Now, if I want to have only P of A given B, if I want to calculate P of A given B, what can I do? P of A given B is equals to, P of B given A multiplied by P of A divided by P of B. I'll just send this to this right hand side, sorry, left hand side. So I'll get P of A given B. Is this formula and this formula both are same? Yes. This is a very important formula. And using this formula, naive algorithm works. This is nothing but Bayes theorem. P of A given B is equals to P of B given A multiplied by probability of A divided by probability of B. And we have, technical terminologies given to each and every component, and you are supposed to remember this. Okay, so the left hand part, P of A given B, is represented as posterior probability. Posterior probability. And P of B given A is nothing but likelihood. P of A is called prior and P of B is called marginal probability. Okay, so I'll use this Bayes theorem formula and let us all involve in calculating, in deriving the output for a use case, a small use case. Okay, so I hope it's making sense. There is nothing complication in this, derivation. How did we achieve this formula? Even if you don't remember, at least if you remember conditional probability, you can achieve this formula. But these terminologies are very important. Posterior probability, nothing but P of A given B. Then P of B given A will be likelihood. So what exactly P given A is nothing but probability of B being true given A is true. So that means event A has already occurred. What you are trying to calculate? You are trying to calculate B, probability of B. Then probability of A, then probability of B divided by probability of B. So this together, all the four components, you're supposed to calculate these three components to get the fourth one. Okay, so friends, even if you remember the conditional probability formula, you can achieve Bayes theorem formula. Okay, especially if you have done any project with respect to naive Bayes, my sincere advice is don't sit in an interview without reading this formula. For sure, you can expect a question, because in general, the interviewers, what they do is they'll start questioning you with respect to your project. Then slowly they'll come into the conceptual part. Okay, as part of conception, as part of concepts, they'll start questioning with respect to the formulas. Not all formulas are important, that's what I see. Okay, but a few are more important. Okay, if something is important, for sure I'm going to, you know uh, time again repeat, so that we'll focus more on it. And Naibase is again a very important algorithm that one has to learn as part of classification algorithm. Okay, right. So now let us together work on a use case and achieve the output. Okay, before that, under Naibase we have types. Okay, there are types under Naibase. What are the types that we have? We have Gaussian, multinomial, Bernoulli. Okay, so when you are actually trying to build a naive model, okay, that y is equals to f of x model that we try to build, okay, so we are supposed to select which type of, naive we are going to use. So what are these three? Gaussian. So Gaussian naive it assumes that all the features are normally distributed. So I'm talking about especially inputs. Okay, so whenever you have, whenever you're working on a use case, you'll obviously have inputs, output. right? So all the inputs should be normally distributed is a basic assumption that Gaussian naive Bayes has. Okay, then when it comes to multinomial, it assumes that the data follows multinomial distribution. Here it is Gaussian distribution, nothing but normal distribution. But multinomial naive Bayes assumes that the data follows multinomial distribution. Okay, so it's nothing but more than two categories. If you have more than two categories, generally everyone is aware of binomial distribution, right? Binomial distribution is generally followed for if the output is having two classes, for example, head, tail, okay, pass, fail. So how many outputs can you expect here? Two. So in such cases, we generally understand how, in order to understand the data distribution, we'll go with binomial distribution. Okay, what if the number of classes are more? We'll go and understand the data distribution using multinomial distribution. So that is a basic assumption that multinomial distribution has. Okay, then when it comes to Bernoulli, it is similar to multinomial, but it assumes that the values are binary, Boolean, especially Boolean. Okay, so for example, present or not present. So if it is present, true. If it is not present, yes, here also it is true. If it is present, okay. If it is not present, it will be false here. Here it is true. Here it will be false. Obviously, right? So this kind of values, this kind of columns represent Boolean, right? So these are the three different types of naives. Okay, and we'll understand more about the types as part of our project. Okay, so we understood the basic, you know, uh, concepts of Bayes, probability, conditional probability, and Bayes theorem. And we also derived how Bayes theorem formula can be achieved, okay, using conditional probability formula. And finally, the types of Bayes. Gaussian, okay. So friends, I'll go to the depth. See, have you ever heard about normal distribution? What exactly is normal distribution? Okay, I see many of you joining for the first time. So we have already covered this particular topics as part of Python to AI playlist. Okay, so we have already completed a playlist for free short-term training on Python to AI. As part of these sessions, I have explained what is normal distribution, nothing but Gaussian distribution. Okay, so what exactly is Gaussian distribution? Gaussian distribution means how many of you go to temples? Maximum, all of us, right? Majority of us, yes. If not, all of us, when we are a kid, probably in our school, there would be a bell in our school. Yes. So, are you able to recollect how the bell shape would be like? Probably like this. When you take a bell, it will be something like this, right? So Gaussian distribution exactly says, you know if the data follows the same distribution, similar kind of distribution, when you try to understand the data how it is distributed, okay, if it is following the similar kind of distribution, then it represents Gaussian distribution. So it's nothing but, this is called as Z curve. If I start explaining, I have to go to the depth. What is Z? Okay, what are the properties? How this is achieved? What is the range? Everything comes into the picture. Okay, anyhow, I'll talk about the properties. If you cut this curve exactly at the center, okay, so these two parts should be identical. That is what Gaussian distribution means. The characteristic. This is one of the characteristic of Gaussian distribution. Then, if you take a continuous random variable and if you're identifying the Gaussian distribution, the range would be around minus infinity to plus infinity. At the center, you'll have mean, median, mode. All of these three will be same. Again, don't will not go to the depth. What is mean, median, mode? So this is all together. We are talking about statistics. Am I right? Yes. So one thing that you are supposed to understand is machine learning, artificial intelligence. Okay, so as part of artificial intelligence, we have machine learning as a subset, and we also have deep learning as one of the subset under machine learning. These three topics, okay, as part of these two, especially ML and DL, we have algorithms, and these algorithms use the concepts of statistics. They are built, these algorithms are built using the concepts of statistics and math topics like probability, derivatives, matrices, then what else? Linear algebra. So, friends, at least if you are good at these topics under mathematics, you can rock in the field of artificial intelligence. Okay, you can rock in the field of artificial intelligence. But when you generally go here and there, what they say is, you should be good at mathematics. No, not exactly. If you are planning to transition your career as part of from a different domain to this domains, okay, so you need not be a professional or you need not be an intermediate guy. At least if you're aware of these topics, you can understand the algorithms when you revise them continuously. Okay, so probably we may not get for the first time, yes, but when you do this for the fifth time, you'll grab what exactly happens under naive Bayes, or not only naive Bayes, whatever the algorithm might be. Then you can apply it on a project. That is what we do. Okay. So when you are a kid, what we used to do, when on a slate, we have practiced the alphabets. Am I right? Yes. So how many times did we practice A? Only one time? No, on the same alphabet we used to you know continuously keep on practicing on the same alphabet. Okay, so this had made us to learn alphabets, then frame words, then sentences. Now today we are able to talk. This is because of lot of practice was done in the groundwork. Okay, at the initial stage we have done a lot of practice. That is the reason we are able to talk, we are able to frame sentences. Then this is also similar thing, right? How can you expect to be completed in one just one time? Okay, so my sincere advice is go through the concepts time again until unless you get confidence that I'm good at naive or whatever the algorithm. Okay, till then you keep on listening to the lectures. Okay, go through the concept again and again, then implement it on a use case, right? So as we go on, I'll try to share more experience that I had, okay, as part of my journey, but I hope it's making sense. Okay, let us not waste our time, and we'll do a use case. So friends, here is a use case. Okay, so how many features do you see? How many columns do we have? I want everyone to interact. Don't sit silent. How many columns do we have? We have four columns. Out of four columns, three columns are inputs. 1 minute. We have four columns and how many rows? One, two, three, four, five. So my size of data set is 5 by 4. 5 by 4. 5 columns, sorry, 5 rows, 4 columns. Out of 4 columns, how many inputs do I have? Input 1, input 2, input 3. So these inputs are generally represented with x, x1, x2, x3. And this is my output. So depending on the three inputs, I have an output. Okay, what are these three inputs talking about? They're talking about temperature, humidity, and wind. Okay, so probably these features are talking about climate. Okay, so is the temperature hot, mild, or cool? Then humidity, is it high or low? Wind, is it weak or strong? We have all the values under these inputs. Accordingly, we have our by column, our output column. Based on these three factors, whether a person is playing or not, yes or no. Okay, so this is the data that we have. Okay, then I'm supposed to use naive Bayes algorithm. So friends, I'm supposed to use naive Bayes algorithm. Using naive Bayes, I'm supposed to predict whether to play or not on the given conditions. What are the conditions? If temperature is mild, if humidity is high, okay, and if wind is weak, then what about play? Will he or she play or not? So for this, for understanding what we have done, we have came up with yes. Even here I have kept the use case well. Okay, probably you may not understand this when you keep going, because I was including a lot of calculations. Okay, so what I have done is I have come up with a word file. Okay, so step by step we'll understand what exactly should be done as part of the calculation, right? So let us use naive Bayes algorithm. Okay, so to determine whether to play or not given the conditions, this is the question: the temperature, humidity, and wind. Okay, right. What is the first step? So if you observe, uh, so this is our formula, right? So what does the formula says? The formula says likelihood P of B given A multiplied by P of A divided by P of B, the marginal probability. So I'm supposed to calculate these three in order to get the posterior probability. Okay, so what does the posterior probability says? The probability says whether your person plays or not given the conditions. So these conditions, the event B has already occurred. Okay, so you are going to check whether a person will play or not. So A takes Y, B takes X. Am I right? See, A and B represents, okay, A and B represents two events, but in our case we have x1, x2, x3, y. Out of these, what have already happened? Inputs already happened. We have the input. So what is supposed to be calculated? Y. So it is nothing but P of y given x1, x2, x3. Am I right? Yes. So you're supposed to calculate probability of y given the inputs. This is what we are going to calculate. Right. So let us go back. So friends, recordings, nothing will be provided. Everything will be present in the YouTube in our channel. Okay. Do subscribe to our channel. Everything will be provided in our channel. Okay, so we are not going to keep them under private. It can be accessed by any of you. Okay, whenever you're free, just go through these lectures time again. Okay, yes. So what is the first step? I started calculating prior probabilities. What do you mean by prior probabilities? This one, okay, better I'll write the formula there itself. The formula says P of A given B is equals to P of B given A multiplied by P of A by P of B. Okay, so this is the formula, and what we are going to calculate, the first step we are going to calculate P of A, prior probabilities. What does A represent in our case? A represents Y, B represents X. And how many X do you have? 3. X1, X2, X3. X1, X2, X3. Okay, so P of A represents nothing but P of Y. So let us calculate the prior probabilities. The first step, let me remove this. Right. So I started calculating the prior probabilities. Okay, in my data set, how many rows do I have? 5 rows. I have 5 rows. That is already communicated, right? 5 divided by 4. I mean 5 by 4. 5 rows, 4 columns. 4 columns, 3 inputs, 1 output. Okay. Out of these 5 rows, how many, in how many rows do we have S under play? In 3 cases, we have, under the play column, we have S. And 2 cases, we have no. So obviously 3 plus 3 is 5. Good. Now let us calculate the prior probabilities. So probability of S is nothing but 3 by 5. Out of 5 cases, how many times do we have S? 3. So probability of S is 0.6. Then probability of no will be obviously 0.4. Why? This was already communicated. Summation of all the probabilities will be 1. So if this is 0.6, that should be 0.4. Simple. So prior probability is calculated? Yes. So we are done with the prior probabilities. What is the next step? Let us calculate, likelihood probabilities. P of B given A. And the question is, should we also calculate P of B? Okay. So this is one thing that I would like to, generally majority of the students, they don't understand, should P of B calculated, the marginal probability? No. The reason is P of B will be constant for all the records. Okay, since this is constant, your value, your output will be dependent only on numerator. It will not be dependent on the denominator. Okay, so that is the reason we eliminate P of B from the formula. Since it's a constant, okay, so this constant will not affect the formula. Okay, if I start explaining why it's a constant and all, it will take a lot of time. Moreover, I should start start the derivation. Okay, why it is a formula and all, there is an explanation, friends. There is a perfect explanation why it is a constant, but because it's a constant, it will not affect the output. Okay, what exactly is affecting the output is the numerator. So that is the reason we generally calculate the numerator and get the value, the output. Okay, so prior probabilities were already calculated. Let us go and also calculate likelihood. In order to calculate likelihood, I am supposed to, use the concept of, what should I use? I am supposed to use the concept of conditional probability. Why? This is representing conditional probability only, right? Conditional probability says P of B given A is nothing but P of B and A by P of A. That is what we are going to do. But I'm going to calculate the likelihood probabilities for all the inputs, okay, taking them separate, taking them one by one. So let me start with the temperature. If the temperature is mild, okay, because this was the question that we had. The question says, what if the probability find the probability if the temperature is mild? So let us calculate, okay, by keeping the temperature as mild for both the cases. Okay, so I'll go and use mild with S and no. What is the probability of temperature being mild? Okay, given the event Y has already occurred. Okay, that means in how many cases we have the play as yes. This is how you can write the formula. Number of mild cases where play is equals to yes divided by total play cases. Play is equals to S cases. Okay, so we have only one case where we have, you know, the temperature being mild and the play is also S. But how many cases we have S? It is 3. Total S cases and a play is 3. So 1 by 3 is 0.333. In the same way, I'll do for, you know, temperature being mild and play is no. So what I'll get? I'll get one more value. In this way, I'll calculate for all the 3 different values. Temperature being mild, humidity being high, and wind being weak. I assume. 1 minute. Yes, wind is weak. So that is the question. From where did you take these values? From here. From here I took the values. Okay. And I'm calculating for both the cases. Play being yes and play being no. Once after calculating these values, what I'm supposed to do? Submit them. Once if you get all the values, substitute all of them in the formula. Right. So finally, applying the Bayes formula. The process is same. Okay, this is what happens in the back end of the algorithm. When you do Bayes, a project, when you build a Bayes model, this is what happens in the back end. So no one is going to sit and do all this process. Everything will be done by your Python script. You're going to use Python, right? Okay, Python as a language. Using Python language, we'll build our model. Bayes model. This Bayes model, okay, when you're trying to build using the Python logic, no one is going to sit and calculate all these things. Okay, we are going to use different libraries, multiple functions are available. Okay, in the backend, the code executes and it calculates all these things. Anyways, let us not deviate. Tomorrow, anyhow, we are going to come up with a project. Okay, a project will be discussed how Bayes model is built on top of a data set. We are going to understand. Okay, but before that, let us complete this session. Right. So let us apply the third step. It's nothing but, finally calculating, substituting the values. Okay, first I'll start with play is equals to s. If play is equals to s, if I substitute play is equals to s, okay, see, observe the formula, friends. The formula says p of a given b. So features are already given. Okay, so let us expand it. P of a, nothing but p of s. A is representing s, right? So p of s multiplied by p of b by a. What is the first feature? Temperature being mild. What is a? S. Okay, multiplied by p of humidity being high given play being s, into again multiplied by p of wind being weak given play being yes. So I hope it's making sense. Don't get confused. Assign the values. Here A is S and B is nothing but features. One by one feature you are supposed to take. Only numerator we have included. If you observe, why there is no denominator? The reason is denominator will be constant across all the records. The denominator being constant, we'll ignore it from the formula. Since we have calculated all these values, substitute them. Once you substitute them, since probability values should lie between 0 to 1. Okay, so when you're trying to multiply a decimal value with a decimal value again, you'll get a very small decimal value. So probability of playing, okay, yes, with the given features is 0.044. 0.044. Now let us do the same for play being no. What if, 1 minute, what if I substitute play is equals to no. Now in this case, A is no and B is nothing but features. That is what we have replaced. That's it. Okay, so do the same process, multiply, you'll get a value. 0.5 into 0.5, 0.25. Then 0.25 multiplied by 0.4 will be zero point 0.1. So 0.1 into 1 is 0.1. So if probability of play being no with the given features is 0.1. So finally, you're supposed to compare the probabilities. Once if you're done, compare the probabilities. So this is what we have got. Probability of S given the features, probability of no with given features. So obviously out of these two, what do you see? Where do you have the highest probability? If you compare these two. Since the probability for no is greater than probability for yes, so the model predicts no. So the person should not play. Is what the model predicts. I hope you got the point. So this is how 1 minute. This is how the model predicts using all the backend calculations. Not even a single calculation will be done by us. But when you try to understand what exactly happens, it calculates prior probabilities, it calculates likelihood probabilities, and it multiplies for all the different classes available, and it compares the probabilities. Once after comparing, wherever there is a higher value, that higher value probability will be returned as output. Okay, so this is how naive algorithm works using Bayes theorem. So what all concepts or what are the applications of naive? Generally that might be the question for majority of us, right? So when you see here, naive is especially used for classification tasks, whatever it might be. You see, spam email filtering. Majority, not only for me, for all of us, will get spam mails. Yes. So in order to categorize whether a mail is spam or ham, that means not ham, not spam. Okay, either it is spam or non-spam. Based on the features, it categorizes the mails. Okay, so this is one of the wonderful use case that Nailbase works well. Categorizing mails into spam, ham. Okay, then if you have text classification use case, if you want to classify the text, okay, you can also do it like task like sentimental analysis, categorizing the documents, classifying the topics. Yes, we can use Naibase. Medical diagnosis. Okay, so giving the probability of a disease present in the patient's body or not. Okay, so upon the patient's symptoms, we'll get the data of the patient, right? So what is the probability that a disease has been attacked to that particular patient or not can be given using NIBIS. Credit scoring. So this is related to banking sector. For the loan approval, what generally bank people they do is they'll go through all your transactions, your CIBIL score, your history and all. Okay, your past as part of bank. Okay, were you paying their loans, EMIs in time or not? Everything will they'll cross check. Okay, and they can actually give you some kind of credit for the loan approval. And weather prediction. So all of these are some of the important applications of naive base. Okay, and naive base simply, I should say, it works on the concept of probability. Okay, under probability, we have a type of probability. It is called conditional probability. Using conditional probability, we have achieved Bayes theorem. So Bayes theorem formula is what it uses. So friends, this is one of the important algorithm as part of classification, supervised learning, and if you are able to grab the concept in the first time, that's okay. But my advice, my sincere advice for all of you will be like, time again go and learn these algorithms. Okay, and not only learning, you are supposed to practically implement them on the data sets. Takes that data sets that are publicly available and start applying the algorithms on the data sets, right? So in the next class we are going to work on a use case for naive Bayes. Using naive Bayes algorithm, we are going to sit and work on a data set. Okay, starting we are going to implement the concept of crisp MLQ. Okay, so we have already discussed this, right? So not all the phases, yes, till evaluation we are going to understand a project, okay, where naibase is implemented, where we are going to implement naibase algorithm to build a model. So this model will be built using naibase. How? What is the approach? What data set we are going to use? What pre-processing steps we are going to learn? What are the EDA techniques that we are going to see? Everything we are going to learn in the next upcoming session. So until then, hold on. Moreover, if you want to, I better suggest you to do some kind of research and gather more amount of good knowledge. And better you also apply on the publicly available data sets. Okay, right. So I'll stop the session here. It was really great. All of us were interacting, and yes. So any questions, friends? Any questions that are related to you know navies? No. Okay. Thanks. Thank you so much. And also do share these important sessions across your connections, whoever is interested in learning machine learning, and also the upcoming sessions that we're going to do on deep learning. Okay. Ask your friends, your connections, whomever it might be. Okay. Ask them to learn these uh, important topics as part of the world. Okay, because these are the important things that are asked when you want to switch your career towards AI. Okay, so whatever you're learning is part of AI only. Okay, all machine learning, deep learning, data science, everything falls under AI. AI is a ocean. Okay, so don't have a myth. So first of all, you be clear on what you are learning. Okay, majority of us are not aware of what exactly we are learning, but it's machine learning we are going to cover as part of these two modules, module 1 and module 2. Machine learning falls under artificial intelligence only. Okay, right. So that's all for the day. We'll meet in the upcoming session. Until then, take care. Have a great day. Signing off. Bye.